Hi everyone, I'm Brinda Venkat, and I'm here today to share the findings from our study. The objective of our research was to understand the significance of linear forces on the knees due to dynamic movements and develop a model to help predict and prevent the likelihood of ACL injuries in non-contact situations. There has been a spike in ACL injuries, especially among high school football, lacrosse, volleyball, and basketball players. Over 70% of these injuries are non-contact related. Literature suggests that the ACL supports 500 pounds of weight, but repeated overuse and accumulation of micro tears over time could lead to a sudden rupture in non-contact situations. Most ACL tears happen as a result of dynamic movements such as jumping, landing hard, sudden deceleration, and change in direction. Our hypothesis was that people with a larger mass will generate more dangerous forces on their knees when they perform jumping movements compared to a person with a smaller mass. This would increase their risk for non-contact ACL injury compared to individuals with smaller masses. To conduct this study, I designed a biosensor using an Arduino Uno coupled with a triple-axis accelerometer from SunFounder. The sensor was inserted into a breadboard and strapped back-to-back with the Arduino with two rubber bands and held together. There were 4 wires connecting the accelerometer to the Arduino. The ground and 5V connections from the accelerometer were connected to the corresponding pins on the Arduino. The SDA and SCL pins from the accelerometer were connected to the A4 and A5 pins on the Arduino respectively. This unit was inserted into a small cardboard box, creating a tight fit so it wouldn't move. A 25-foot USB cable was plugged into the device to provide power. This device was strapped with Velcro just below the knee of the individual participating in the experiment. Each trial involved the subject going into a partial squat and then jumping as high as they could and landing back down on their 2 feet. The accelerometer recorded the g-forces along the 3 axes. The anterior-posterior direction matched the z-axis of the accelerometer and was perpendicular to the plane of the accelerometer and the position below the knee. Since this location was very close to the knee, we assumed that this force acted perpendicular to the knee as well. This conformed to the Fx axis of the free body diagram shown in the figure. The g-forces along the lateral and compression axis were not substantial, and we assumed there was little to no impact from the linear forces along those axes. While the rotational forces could play a major role along those 2 axes, those forces are not the focus of our study. I included 2 subjects in my experiment, with individual 1 having a mass of 75 kilograms and individual 2 having a mass of 50 kilograms. Each subject performed 7 trials. This particular dynamic motion was selected since, according to the literature that was researched, this movement is one of the non-contact movements that is known to affect the ACL. Our experiment was conducted safely, ensuring that individuals warmed up and stretched so that subjects would not injure themselves while participating. After every trial, we checked whether the subject was fine. We also checked the strap device and ensured it was securely in place for the next trial. My device measured the g-force as a number in terms of a multiple of g, the acceleration due to gravity. We converted this to the actual force in newtons by multiplying with 9.8 meters per second squared and the body mass of the individual. A person's mass will influence the calculated value of the force, and we assumed that this is a result of varying ground reaction forces dependent on the mass of the individual jumping and the effort with which the jump was performed. Understanding forces exerted on the knee in terms of multiple of g, and then computing the actual forces in terms of body weight enabled the creation of a generic model, which could be personalized and applied to each individual based on their own mass. We created a negative control group by asking individual 1 to walk leisurely and computing the forces on their knee. This leisure walking does not cause knee injuries in healthy individuals. There were 3 groups considered in our experiments. We applied a one-way ANOVA to the collected data. This yielded a p-value of 0.01167 times 10 to the power of -3, showing statistical significance in the data. We then performed multiple comparison tests, 3 t-tests to be exact, between the 3 sets of data. We could see statistical significance only between situations when an individual jumped compared to the negative control of leisure walking. However, we did not see any statistical significance between individuals of 2 different masses and the forces generated on the knee due to jumping. So we had to accept the null hypothesis in our results. While the forces generated due to jumping are significant in magnitude compared to the forces generated while walking leisurely, we cannot conclude that individuals with larger masses will have a greater risk of non-contact ACL injury just based on measuring the linear anterior forces generated on the knee. This research study showed some limitations in our approach. We only considered linear forces when rotational forces also play an important role in ACL injuries. We did not take into account that different body types and the body mass index, or BMI, which are more relevant than just the mass of a person. Mass is made up of body fat and muscle. The height of a person, bone density, hip rotation, knee flexion, and other genetic considerations may also influence the risk of non-contact ACL injuries. Whether the individual is male or female, and even someone forgetting to warm up correctly could be contributing factors as well. An immediate future step I plan to take to improve my design is to incorporate an inertial sensor and take into account rotational forces along 3 axes in my model, in addition to linear forces as well. Thank you, Johns Hopkins University, and all of my instructors and teachers for this memorable opportunity. Thank you to all my peers as well for the wonderful discussions, positive feedback, and helpful suggestions that allowed me to improve my understanding and make my work even better. I really appreciate this very much and look forward to future interactions.